Okay, let's talk about how we express uncertainty in measurements. Now, no measurement has 100% accuracy. You're limited by your tools, you're limited by the precision of a ruler you use to measure length. In fact, there's even fundamental physical limits to how well you can measure stuff. In quantum mechanics, there's this uncertainty principle that says that you can only measure things with a certain amount of precision, no matter how good your tools are. So there's always some amount of uncertainty in any measurement you do. And you don't want to make people think that your results are more accurate than they really are. In science, we want to be honest about what we are presenting. So we need to express measurements with the right amount of certainty and the right amount of uncertainty. The real way to do this is through a process called error propagation. That involves using calculus, and it is overkill for what we're doing in this class. But if you're doing physics research that needs to be published, this is what you'll have to do. In textbooks, we do this kind of shortcut way. It's ballpark, it's rule of thumb. It's pretty good. It's called significant figures. You've probably seen this if you've taken chemistry before. And the idea is that when you write down a number, the final digit on the right is the precision of your measurement device. You only express as many digits as your device lets you measure precisely. And when you do calculations with numbers you measure this way, we have two rules of thumb. If you multiply them, you keep the same number of digits as in the least accurately known quantity. And if you add them or subtract them, then you keep the same number of decimal places as in the least accurately known quantity. For example, let's say we want to multiply 4.822 meters times 5.1 meters. Now, if you just type that into your calculator, you get this answer 24.59 meters squared. But let's look at our rule for multiplication. In our final answer, we should keep the same number of digits as in the least accurately known quantity. Our least accurately known given quantity was 5.1 meters, which has 2 digits. So in our final answer, we should express it using just 2 digits. So you take this answer and you round it to the nearest 2-digit answer, which is 25 square meters. Let's do an example with addition. Let's say we have 123 seconds plus 5.35 seconds. Your calculator will tell you 128.35 seconds, but we need to use this rule for addition, where we keep the same number of decimal places as in the least accurately known quantity. So what we mean by that is the number 123 doesn't have any decimal places after the 3. This is less precisely known. So we need to throw away all the numbers to the right of that decimal point. So we have 128 seconds. And one final comment is that when you're writing numbers and you want to indicate how many significant figures, it's usually good practice to write them using scientific notation, because that can be more clear to indicate the number of significant figures that your number has. So let me show you just a few examples of scientific notation and how it helps us communicate significant figures. Let's say we have the number 1,234. This number has 4 significant figures, and written in scientific notation, it would look like 1.234 times 10 to the third. Let's say we have the number 500. Now, 500 is kind of a weird case. It's a little bit ambiguous because when you have zeros on the right of that number, we don't necessarily know whether they're just placeholders or whether they're things that we've actually measured. So in order to remove that ambiguity, it's better to write a number like this in scientific notation. So let's say that 5 really is the only significant figure there. It would be better if we wrote this number as 5 times 10 to the 2. Now it's clear that there's just one significant figure. If you have zeros after or zeros to the right of a number, and they're also to the right of the decimal point, then they are significant. But again, you can remove any ambiguity in trying to read that number by writing it in scientific notation. So this is 5.00 times 10 to the minus 4. So I encourage you to express answers in scientific notation whenever possible, because writing numbers this way lets you clearly communicate how many significant figures it has, and leaves out any ambiguity that the reader might come across.